All right, again, welcome to today's lecture. Today we will be addressing the remaining degrees of freedom in molecular systems. Last week we were talking about Hartree-Fock and solved the electronic part of the Schrödinger equation. And so today we will pick up on that and look at rotation and vibration. So I'll start with this first slide here, page 132. Let me see if I can get this full screen. Okay, so what have we covered? So far, if you look in terms of energy where we're standing, electronic excitation, meaning rearrangements of our electron structure, are in the range of a few eV, or in terms of wavelength, in this regime of visible to UV light. So that's for electronic excitations. And having solved for not just the electronic ground state of a molecule, but also for these excited states, we can take in the first approximation our vertical energy differences, for example, between, say, our electronic ground state at the equilibrium position and some other electronically excited state, to estimate the energy that's necessary to excite the molecule electronically in the picture of molecular orbitals, to take an electron from an occupied orbital and promote it to some previously unoccupied or virtual orbital. Right, so now we're gonna talk about the degrees of freedom that remain due to the fact that we have a molecular system where the atoms themselves can move. And I will follow an approach here that is taken from Haken-Wolf and is, so to speak, our first contact with these nuclear degrees of freedom in a mathematically precise sense for the diatomic molecule. And it goes as follows. I mean, obviously, we have already sort of made a coordinate transformation when speaking about the Hartree-Fock procedure, where we said, okay, for a diatomic, the only degree of freedom in terms of nuclear motion that plays a role for this molecule is the internuclear distance. So it's effectively only one coordinate. But let's do it in a more strict sense and really try to work this out in a, say, for example, Cartesian basis, where we address each of the nuclei and the electron in this given laboratory frame. How would we get to this result that our only relevant internal degree of freedom for molecular motion is this internuclear distance? And this goes as follows. We start with a product ansatz for our total wave function. And now you see I'm speaking of the total wave function, not of the total electronic wave function, because I'm addressing all the particles in our system, nuclei as well as electrons. So we write this as uppercase psi as a function of r, and then r1 and r2. These are now Cartesian coordinates for the electrons and the nuclei. And we write it as a product function of psi in math font times phi, and phi is only a function of the nuclear coordinates. So we said we can separate the motion of electrons and nuclei. So we have applied the Born-Oppenheimer approximation, and we assume that the electronic part has been solved already. So if we just take those parts of the Hamiltonian that concern electrons and solve this, we get the corresponding eigenenergy. And this is obviously a function still of the nuclear coordinates, because it is our potential energy surface. And we can write this as a function W, which is a function of the nuclear coordinates R1 and R2. So if I look at the remaining part of the Hamiltonian, I end up with this equation here, where I have my kinetic energy operators for the nuclei. Then I have the so the interaction, the Coulomb interaction between the two nuclei, and our potential term, our potential energy surface, which is due to the fact that we have these electrons in a certain density distribution around our nuclei, and this energy of these electrons, or their contribution to the total energy, is dependent on the actual nuclear geometry. So this is our W R1 minus R2, and I'm already writing this here also in the argument of W as R minus R2, because the next thing we are doing is a transformation in terms of variables. We transform from our absolute position coordinates, where we had in our laboratory frame x, y, z coordinates for each particle in our system, into a coordinate system which consists of center of mass and relative coordinates. Okay, so in the case of the nuclear Hamiltonian, it's R1 and R2, and now we transform into Rs and R, with R denoting the difference, so this is just a vector then pointing from one nucleus to the other, and Rs, which is the absolute position of our center of mass for our diatomic molecule. And so we get Rs given by this formula, with Ms as the total mass and Mr as this reduced mass, which is the product of M1 with M2 divided by the total mass, M1 plus M2. Okay, so that's our transformation. We can take derivatives, we take the second derivatives as well, and translate our nuclear Hamiltonian from R1 and R2 dependence into Rs and R dependence, and obtain an equation that looks like the one here on the first in the first line, where we have also combined our electronic contribution to the potential energy with the Coulomb interaction between the two nuclei. And we write this as a potential V of R, with R denoting the relative distance between the two nuclei. So this is the internuclear distance, right, that we introduced here. And now, after this transformation, we see the following. The potential term that appears in our Hamiltonian, this V of R, is not a function of Rs, right? So it's not dependent on the actual center of mass of the total system. So if I make a product ansatz, I can translate the translational energy component from the rest, because the translational energy is not of spectroscopic relevance. So we can separate it out by saying our wave function, our nuclear wave function in coordinates Rs and R is simply an exponential function e to the ikrs multiplied by some yet unknown function chi of R. How do we get this solution e to the ikrs? Well, if you look at the Hamiltonian in the first line, and you just take those parts that are relevant with respect to our center of mass coordinates, you can see it is the Schrödinger equation for a free particle, right? Because the potential V is only a function of R and not of Rs. So it's a simple second order differential equation, which we can solve by finding by twofold integration. So we end up with the usual result, an exponential function. So if you take this solution and you put it into the equation, giving you the two, so if you take the second derivatives, you can see it complies and is solving the Schrödinger equation. The corresponding total energy is then this energy that we would like to. So we can say the total energy then consists of the unknown part and a part which stems from the motion of our molecular system in space. So if you open any quantum mechanics book and you look at the solution for the Schrödinger equation, how it is done for a particle, you can, due to normalization constraints, you can do it for a particle in a box and then extend the box size. You get these known results as it's written here on the slide. And we are done with the translational part and can focus now on the remaining part, which is our chi of r, with r denoting the difference, so the relative position or the relative distance between the two nuclei. Here we once again do a separation, so we write this chi of r now as a function of r, where r is now denoting a scalar value, namely the distance, multiplied by a function which is only dependent on the angle theta and phi. So we transform to spherical coordinates for the description of chi of r, which is the only part of the nuclear wave function that is actually relevant for the actual energy of a molecule somewhere in space, since we are not in an external field, right? So translational aspects don't play a role. There might be some energy in translation, but it's spectroscopically not relevant for us. So the whole information that we are interested in is in this chi of r, chi as a function of r, with r denoting the difference of the distance between the two atoms, and we switch to spherical coordinates to take advantage of symmetry. Now, what we can do is, when doing this transformation from r to these spherical coordinates, we have to translate our differential operator, right? So the Laplace operator that appears here has to be translated into spherical coordinates, and it has this shape. You can look this up in any maths formula collection to make this transformation. You end up with a series of differential expressions. So we obtain a Hamiltonian now as a function of r, theta, and phi that looks like this, where we have also introduced L as the angular momentum of our diatomic system. And so this is just something you've learned before in quantum mechanics, or which you have seen before when, for example, solving the Schrödinger equation for the electron in the Coulomb field, that a part of this operator, of this nabla squared operator, when translated into spherical coordinates, is actually the operator for the angular momentum, because in a spherically symmetric situation, that would be a conserved quantity. And so this part comes in as L squared, here written as in operator shape. And we have only one part that remains explicitly written as derivatives with respect to r. Okay, and on the right, or on the function itself, this chi has been rewritten as a product of a function f, lower caps f, with uppercase f. So f times f is now representing our chi. Now, since L corresponds to the angular momentum operator, we can take advantage of this by choosing f to be an eigenfunction of L and of Lz. So of L squared and of Lz. So if we assume that our nuclear wave function is of this form, then we can simply replace the operator by the corresponding eigenvalue that belongs to the value of the angular momentum in this case. And so instead of L squared, we have then h bar squared times j plus 1. This is the corresponding eigenvalue for the total angular momentum, L squared, and the corresponding eigenvalue for the LZ operator is simply h bar times m. And since we're denoting here a angular momentum for the total system, I'm using uppercase letters here. So our orientational or magnetic quantum number, so to speak, for the real rotational angular momentum of our system is denoted as uppercase M here. Okay, so with this, we obtain now an equation. So the remaining part of this Schrödinger equation for the nuclei looks now like this. We had this derivative, second derivative with respect to r. Then we have one first order derivative. Then we have our term where the angular momentum came in. This is nothing but, if you look at it, it is basically L squared over, and m times r squared is the moment of inertia. So what's written here is simply the energy that is in the rotation of the molecule. And depending on its angular momentum, which is represented by the eigenvalue J, you get an energy which is quadratic in J. It's J times J plus 1 times h bar squared, and so on. Right, so these are the contributions, and the last term is this V of R, the potential term, so the electronic energy as a function of the internuclear distance. And okay, so right, we would like to solve now this differential equation, or what is this eigenvalue problem actually to obtain a set of energies and corresponding eigenfunctions f. And well, we see that due to the fact that we have a derivative here with respect to the internuclear distance, and we have a term that includes the rotational energy, we see that the total energy of the molecule contains two contributions, right? One is due to a change in the internuclear distance. That's something we will refer to as a vibrational aspect or vibrational part of the energy. And for a given internuclear distance, we will have a certain moment of inertia, and therefore our rotational energy will depend on the angular momentum, but also on this moment of inertia. And this means that the two types of motion that are possible for this diatomic system, namely its rotation and its vibration, are coupled. However, if we assume that this first derivative, d over dr, is something of minor importance, so that this second term contribution is small, right? So that the contribution or the change of the energy with respect to a change of the internuclear distance is small compared to the other terms that we have in this equation, we can just leave it out. And if we to make things easy, if we assume that we don't have any angular momentum in our system, then this equation boils down to something that is very easily solved. So this means if we remove this term here, because we say it's negligible, and we have this term set to 0 because J is 0, we say there is no angular momentum, what kind of equation are we confronted with? We have just a second derivative with respect to the internuclear distance, and we have this potential term. And if I make now this approximation that we are dealing with a molecular system around its global minimum, I do a Taylor series expansion again, and the first contribution or the first term in my expansion is 0 because it is a expansion at the extremum. So the leading term is the second. So we can write this second derivative as k, the curvature, and we see in this approximation it is a quadratic potential. And this means for our remaining degree of freedom for this vibration that we will end up with what type of solution here?
An harmonic.
Yes,
oscillator.
exactly, with the harmonic quantum oscillator. Right,
Can I ask something about that?
sure.
You just argued that you kick out the second term because you assume that the variation with respect to r is quite small.
Mhm.
Why then do you keep the first term? I mean, this contains the second derivative with respect to r.
Yes.
And you argue that even though the variation with respect to r is small, the curvature isn't?
Mhm. Well,
Because I would have thought that if you kick out the second, you should also kick out the first term.
no, because if you think about it, you're expanding this now all at the position where you have a minimum on the potential energy surface, and at the minimum,
Okay.
you see the second derivative has some value. It is exactly the curvature of the parabola that you fit into your potential, but the first derivative vanishes. So this is why it makes sense to expand it this way, and why you can argue that also anything that depends on the change with r in first order is negligible. Okay, but you're right that in a sense it is an approximation, and we lose some accuracy the further we go away from the equilibrium, and we will have an effect that's obviously coupling the two ways of how energy can be stored in the system. Because if you have a system and you think of it rotating, then if you're in this rotating system, then you will feel this centrifugal force, right? So this will open up, and this means it will change from your equilibrium position simply through rotation. But this also means that if you think of these two particles being connected by a spring, that the spring is slightly pulled apart, and therefore you deposit energy in vibration, basically in the spring by pulling it apart. So this is how these two are communicating, basically rotation and vibration. But in a first approximation, we can say that this is negligible. So we set it to 0, and we obtain this as our final equation. You have correctly identified it as the harmonic oscillator in one dimension, because this is only the internuclear distance. We write it as r, and I can immediately solve this. You have done this in quantum mechanics before. We know, for example, how the ground state eigenfunction looks like. It has this Gaussian shape. We have in the past also discussed the set of special functions, which are solutions of the harmonic oscillator, the Hermite polynomials, then multiplied with this exponential term. So that's how it's working. And we know the corresponding energies. If it's a perfectly harmonic potential, then the energies would be equidistant with E nu equals nu plus 1/2, and this in brackets multiplied by h bar times omega. So we have equidistant spacing in terms of energy. And even for nu equals 0, we have a non-vanishing energy, as we have been discussing before, due to the Heisenberg uncertainty. But you see, here we just started treating the system in a more rigorous way by starting in Cartesian coordinates for our two particles and for the electrons. So we had quite a few degrees of freedom. And in this stepwise procedure through the product ansatz, our trick of getting rid of the translational part, then just focusing on these internal remaining degrees of freedom and rewriting the problem in spherical coordinates, we could make another product ansatz, identify an angular momentum part, and introduce this angular momentum quantum number, then say, okay, if this is an eigenfunction of the angular momentum, we only have to deal with the radial part. And here we see what remains is the harmonic oscillator in this approximation, which is valid for small variations with respect to the equilibrium position of the two nuclei. So we get our total energy expression by taking all these contributions and note the nice color coding, which should be consistent with previous slides. So we said electronic energy is our energy due to differences in the potential energy surfaces when I'm plotting the ground state, the excited state. So in the diatomic molecule, these were these curves that we plotted. And so each of these curves has a is a corresponding, or is giving you corresponds to a different electronic structure. So the ground state the lowest, and then we have this electronically excited state. So this is the first contribution. Then in each of these potential energy surfaces, which are curves in our case for this diatomic molecule, we start with the harmonic approximation, and we know then in these harmonic potentials how the energy depends on the actual curvature of our parabola. So this is coded in this omega, because omega is square root of k over m, with k denoting the actual curvature, so the second derivative with respect to a variation in r. And the last term was this energy contribution that stems from the rotation that the molecule can perform. And we can classify it with respect to the quantum number J, which tells us the angular momentum of rotation in this molecule. And that means we have all the energy, the most important energy contributions covered that our diatomic molecule has. Electronic energy, vibrational, and rotational energy. And in this order, it's also going from largest energy differences to smallest energy differences. Okay, so that's that. And now we are going to generalize this a little bit and make the switch from diatomics to polyatomic molecules. First, by looking at rotation. Again, I should mention that this follows the book of Hertel Schulz now. So this is on page 89, I think. Yes, I have written it here on page 89 of Hertel and Schulz in the second book, where it goes a bit more into detail with regards to polyatomic molecules. So for rotation in a polyatomic molecule, we have to realize that our moment of inertia for the system is a second rank tensor. Because if you think about the simple formula, say L equals I times omega, then I only appears as a scalar in more or less exceptional cases, right? Because it's not necessarily correct that the axis of our rotation and the axis of the angular momentum coincide. So if we have some arbitrarily shaped object and we give it some spin, then this means that we will introduce two things. On the one hand, we have this rotation and we have an angular momentum, but we also have the centrifugal forces acting, which appear in the second rank tensor of the moment of inertia as these non-diagonal elements. And so if you write down this tensor, I with I and j as the indices, then it has on the diagonal this mk times k rk squared, and then these coupling terms, the non-diagonal terms, which are these products. Okay, so that is the connection between our rotation described by the vector omega and the angular momentum here written as n. And I'm not intentionally trying to confuse you by introducing yet another letter for angular momentum, but we have already used quite a few, and we have to stick to some kind of convention. And it's very common to denote the real angular momentum, so the angular momentum of the physical object molecule in space as n, because L is something we've used already for the angular momentum of the electron hull, if you remember, right? So let's not stick with this one and try out a new one, which is written as n. So we say n equals I times omega. This is a little bit sloppy in the way it's written, because in this way we have to realize that omega and n are vectors and I is a second rank tensor, which is explicitly visible here in this situation where we say, okay, if I would like to know the moment of inertia for some arbitrary rotation, say a rotation along some vector r, then I will get the corresponding angular momentum by taking the second rank tensor I and then multiplying it from the left and from the right with this corresponding unit vector of the direction of rotation that I'm interested in. Okay, so I let this matrix I, so in matrix, you can write this as a matrix acting on the vector. If I write this vector in Cartesian coordinates, for example, this gives me another vector, and then I come in from the left with a transposed unit vector from the left, multiply it onto it, and I get a scalar, which is the moment of inertia for a rotation along this given axis with vector ER. Now, in order to classify and to handle this in a straightforward way for all kinds of molecules, we will do the following. We will proceed by defining principal axes that can always be found, namely by the diagonalization of our tensor. So this tensor in Cartesian coordinates is this matrix, and so by diagonalization of this matrix, I'm getting the three eigenvalues, and these are the corresponding, or the corresponding eigenvectors are the ones that I'm choosing. Basically, you can think of it this way: I'm doing a rotation, right? I'm doing a linear transformation. I rotate my coordinate system in such a way that in this new basis, my matrix becomes diagonal, and this is shown here on the in this little graphics here. We have some molecule, and what we do now is we look at its moment of inertia, and we diagonalize this tensor. We end up with new coordinates, which we denote as A, B, and C, and they are aligned in a way which corresponds to the maximal or to the external ways values of the moment of inertia, right? So for each object in 3 dimensions, I can find this 3 axes, and I will use these 3 axes as my reference axis in the molecular system. So I'm getting these 3 values. I'm giving these values names, IA, IB, and IC, with the convention that IA is the smallest moment of inertia. And so if I am now interested in the moment of inertia for a rotation along some arbitrary axis, then in my newly defined set of coordinates, I can say that this moment of inertia is simply a sum of the moments of inertia along this new axis, so that this values A, IA, IB, and IC, multiplied by A1 squared, B1 squared, C1 squared. So I'm basically simplifying this a little bit, and visually it means that I can do one more step. If I define a new coordinate saying this is, we switch from some A1, B1, C1 to a new coordinate A, which is simply the original coordinate that we obtained from this diagonalization, but now also rescaled by division through the total, through the moment of inertia, square root, I'm getting this expression here. What's so good about writing this in an implicit form? We can see this is some surface, because this is an implicit function of A, B, and C. If it was same values everywhere, then it would be a sphere with radius 1. So all the points on this sphere would be covered by this implicit function, right? Now A, IB, and IC are different, so it's some more or less squeezed shape of this sphere. And the good thing about thinking about moment of inertia in this frame is that we can immediately see what's the actual value of the moment of inertia for a given vector by just looking at this shape in space that we obtain here. So this basically ellipsoid structure of the moment of inertia in our coordinate representation. If I'm just drawing some arbitrary vector from the center and make it go through the surface at some point of this kind of egg-shaped surface here, I can read the actual value of the or I can directly derive the actual moment of inertia that I have for a given positioning of my rotational axis. So the funny thing about doing it this way is that the shape of this ellipsoid is sort of a simplified actual shape, or corresponds in some way to the simplified shape of this physical shape of this actual object that we are working on. Because, for example, if you have if you think about this object rotating along the c-axis, then the way it's shown here in this picture, it seems that this would be the axis where we have a maximum of moment of inertia if we really think of this egg as the actual physical object in space filled with some mass. See, if I rotate it along the c-axis, this would be the axis with the largest moment of inertia. And since we are scaling with respect to the inverse of the square root of the moment of inertia, this fits to the actual structure, because when this vector c is cutting through our egg shape, it cuts at this point, and you see here the distance from the center is smaller than it would be, for example, for cutting through along the a direction. And since it's the inverse, this means that for a rotation along the c-axis, we have a much larger moment of inertia than we have for a rotation along the a-axis, okay, because of this inverse relationship. And therefore, this abstract picture of the moment of inertia ellipsoid here in this diagram fits, so to speak, also to some extent the actual shape of the molecule we're working with. This is going to be important on the next slide when we talk about real molecules, which can be of any shape, spherical, maybe a little bit pancake-like or more cigar-like in shape. So that's what we're going to discuss now, but we just need to have a clear system of reference. And here we have two choices. We can always refer to our system, coordinate system in our laboratory frame or in a space-fixed frame. But we can also use now this body-fixed system where we take these vectors A, B, and C as we have derived by diagonalizing the moment of inertia tensor. And since we are talking about angular momenta, we have this standard algebra. We can say that if this is our total angular momentum n, then n squared has the corresponding eigenvalue h bar squared times n plus 1. And obviously, the angular momentum as a vector with a given length must be the same in the space-fixed system as it is in the body-fixed system. But what's different is the reference with respect to orientation. Because in the space-fixed system, I would typically choose the z-axis as my reference and look at the projection of the angular momentum onto the z-axis. So if we write nz as the z component of the total angular momentum of the rotation of our molecule, then it is h bar times m. So here we use this m in the space-fixed system. And in the body-fixed system, we will take our axis c and look at the projection of the angular momentum on this axis c. I go back one slide to remind you what was the axis c. So we said c was the axis with the largest angular, with the largest moment of inertia, right? By our definition. Okay, so these are our two references. One is our laboratory frame with the z-axis, and one is the molecule or body-fixed system, which is uniquely determined by giving the length of the angular momentum and its projection onto the z-axis. And as usual, we have this variation. If we have n, then we have 2n plus 1 possible orientations of this quantized vector going from minus n to n. Same for m and for k. So what's now the big advantage of the body-fixed system? Well, in the body-fixed system, we have the advantage that our moment of inertia tensor is diagonal. And so if we look at the rotational energy, it is a simple sum of the contributions for the projections of the angular momentum on A, B, and C. So I can say the rotational energy is simply our angular momentum component squared divided by 2 times the moment of inertia. And we will then introduce or collect all these constants like Planck constant and our parameter, which is given by the actual structure or geometry of our molecule, which leads to a given moment of inertia. We will absorb this into the so-called rotational constant. So I'm just writing this prefactor that appears. Let me go quickly back to where we spoke first time. See, so this angular, or this part here, in the diatomic case, the moment of inertia is simply this reduced mass times r squared, right? So this would be the moment of inertia for this diatomic system. And what we do in the diatomic case is we simply take h bar squared divided by 2mr and re squared as a constant b, which is specific for this molecule and which we denote as the rotational constant. And then our energy expression for rotation is very simple. It's just b times j plus 1. Okay? And since these energies are comparably small, we said it's in the range of a few tens of wave numbers, it makes sense to have it already expressed in wave numbers, this constant b, right? So this is a very common thing in spectroscopy, to write these rotational constants not in the unit of joule, so not in an SI energy unit, but instead in centimeters to the -1. This is why A is here defined as h bar squared over 2 times moment of inertia and divided by h times c. Because by dividing through this h times c, I'm ending up with a value for this constant in units of inverse centimeters. So if it's like this, I would have it in inverse meters, and then I have to also convert it into centimeters by this factor of 100. This is very common in spectroscopy to refer to these energies in the unit of wave numbers. Okay, so that's just how it goes. So this is our approach in principle, and now we have to discuss it for the possible ways of how our molecule can be shaped. We will distinguish 4 types of molecules, starting with the one that we had already discussed before. The diatomic is in the class of linear molecules, and here we only have this one rotational constant b because we have only one moment of inertia, right? So it's only this reduced mass multiplied by r squared for the diatomics, for example, giving you the moment of inertia, defining you your rotational constant, and you have this energy b times n plus 1. And you can see in this notation here, if we write b as something in the units of wave numbers, then we have to multiply it again with hc to have something in the unit of joule for SI, right? So this would be the real expression for the energy in joule if we have b defined as something in the units of wave numbers. Okay, this is the linear molecule. So what's happening in the case of spherical molecules called spherical tops? Yeah, so top in English, it means like Kreisel. So the spherical top is a molecule for with a very high symmetry, and we will be talking about symmetry groups at the end of this lecture series, at least a little bit. And those symmetry groups which have a lot of symmetry elements, so meaning that these are describing molecules that have many elements of symmetry, so they are highly symmetric. They typically have a situation where all 3 of my extrema of the, or eigenvalues of the moment of inertia tensor are identical. So the most obvious structure that fulfills this shape is, of course, the sphere itself, right? So it doesn't matter how we place our angular momentum in space with respect to some position in the sphere. Everything that goes through the center of the sphere gives us the same moment of inertia for rotation. So we can expect a very high degeneracy in this case, and the energy looks exactly the same as it does for the linear molecule. We simply have a term, it looks basically identically. We have B, the rotational constant, then this h times c, so to have it converted into joule again, and then n times n plus 1. The only difference is how we calculate B. B is again our rotational constant, which is basically inverse to the moment of inertia. And for the spherical molecule, we have to know its moment of inertia. It's not just simply this internuclear distance in a diatomic, for example, multiplied with the reduced mass. Here I have to explicitly evaluate at first this moment of inertia, but if I know it, I know everything about rotational energy spacing in the system because of this high symmetry of the molecule, right? So it's again just B times n plus 1, and B contains the moment of inertia, which I have to calculate in this case. Right. I've also denoted here something about degeneracy. And that's an interesting thing. In a spherical molecule, and to give you have it, give me a second, I'll show you. So I give you an example of a spherical molecule, or a spherical top, let's put it this way. Just have to build it for you quickly. Okay, now I won't build this one because this is part of the quiz at the end. I built something different, but which is also symmetric enough to be a spherical top. Let's have a look at this molecule here. Okay, it's obvious that no matter how I position my axis of rotation here, so I can pick, I can take any positioning of the angular momentum. It will always have the same moment of inertia. And I have now this effect that it doesn't matter how my vector of angular momentum is positioned with respect to some internal symmetry axis, which I pick as my axis of reference. For example, this bond from the center atom to this H is my reference, my figure axis, for example, for this structure. And no matter how the angular momentum is oriented with respect to this axis, it doesn't change the energy splittings of rotation, right? It doesn't matter. So we have this internal degeneracy, which gives us 2n plus 1 possibilities of how it can be orientated without change in the actual energy. But I also have now a second degeneracy, because even if the molecule is now arranged like, or the angular momentum is sitting like this, and this is my reference here, it doesn't matter how this reference axis, this connection between the center atom and this hydrogen atom here, is placed with respect to my z-axis in my laboratory frame. So this gives me another degree of possibilities or of freedom with respect to how this figure axis can be arranged in space with respect to my z-axis in my laboratory frame. So for the spherical top, I have this twofold degeneracy, 2n plus 1 times 2n plus 1, because it doesn't matter how the angular momentum projects basically onto my reference axis inside the molecule, and it doesn't matter how the molecule is oriented in space with respect then to my reference z-axis, for example, in the laboratory frame. So I have 2n plus 1 times 2n plus 1 possibilities, which are all same in energy. So this doesn't affect the energy, but it has a consequence for the line intensities, because if I have a lot of degeneracy for a given state, it means that many of them can be populated at the same time. So their probability is affected, and therefore the spectrum or the intensity distribution is affected by these features of degeneracy. So that's the spherical top. Let's move on to something that's slightly more complicated, but only on first sight, the symmetric top. A symmetric top is a molecule where we have two of the three eigenvalues of the moment of inertia tensor being equivalent. And this leaves us two situations. The two that are equivalent can be those with the higher value or can be those with the lower value. If we have a molecule where after diagonalization we have two eigenvalues which are identical and which are the larger ones, then the shape of our molecule is something we will describe as prolate. So it's this Sigger type shape. And this is where this analogy between our ellipsoidal representation of this moment of inertia surface comes in handy. It is basically related to the actual shape of the molecule. Look at this figure here, denoted as A, the prolate case. You can see that a rotation along the z-axis is giving you the same moment of inertia. So think of this as like an egg shape, right? So this is a sort of an egg shape. If you rotate this now along the z-axis, it has the same moment of inertia as a rotation along the b-axis. And these two rotations are rotations with a higher moment of inertia than a rotation along the a-axis, which is this figure axis of this egg-like shape, right? So this also fits to this description of this tensor surface that we have discussed before, because we said that we have plotted this sphere, this surface structure in coordinates which are scaled by 1 over the square root of the moment of inertia. That means that if the distance between the center and the surface is small, then it means it is a larger, because it's inverse, it's a larger moment of inertia. And if the distance between where the vector cuts through the surface and the origin is large, it's a smaller moment of inertia because of this inverse relation. So these both pictures fit together, which is a nice feature when it comes to mnemotechnics, basically, to keep this stored. Okay, so that's the prolate situation. And in the oblate situation, we have two moments of inertia A and B, which are equivalent, and these are then the smaller ones. So the oblate is the pancake type structure, right? So we have we can think of it as a pancake, and we have one axis where the moment of inertia is larger. This would be this z-axis in our case here. And we have two other axes, A and B, where it is smaller. This would be in our pancake analogy axes, which are in the pancake plane. Right? So these two axes, orthonormal to each other and in the pancake plane, are the ones with the lower moment of inertia, and the one which is perpendicular to the pancake plane would be the one with the larger moment of inertia. Now, in these two cases, our expression for the energy with respect to the rotational quantum number is slightly more complicated, but we can easily derive it. We do it here for the symmetric top with a prolate configuration. This is what we will obtain. It is energy as a function of n, the actual angular momentum, and k, which is the projection of the angular momentum onto an axis. And here, for the ProLight type, we will choose the projection onto the a-axis, because this axis is uniquely defined. It's the one that has the lower moment of inertia, right? The other two have the higher moment and are identical. So how do we get to this energy expression? Well, we write down our energy expression as follows. The rotational Hamiltonian has these components: nb squared, so this is the projection onto axis b, squared over 2ib, with ib denoting the moment of inertia for the rotation along the b-axis. Then I have the same for the c-axis, and since b and c have the same moment of inertia, it's nc squared over 2ib. The only problem is that a is different, so I have plus na squared over 2ia. And in order to simplify things, we just add a na squared over 2ib to this equation, and also subtract it at the same time. So we are adding a zero basically here in this equation. We add the expression na squared over 2ib, and then we subtract it again. Why? Because then we can collect the terms na squared plus nb squared plus nc squared over 2ib, and just write it as the total angular momentum n squared over 2ib. And the other term has then to be put together with the term for the a-axis. So it's the na squared multiplied by 1 over 2ia minus 1 over 2ib. And this factor, this 1 over 2ia minus 1 over 2ib, is something which translates into a simple difference of the rotational constants a and b. And this na, this is the projection of my angular momentum onto the a-axis, and I'll denote this as the projection or rotational say orientational quantum number, in this case with respect to my axis a, as k. Okay, and so in this case then my total rotational energy has this first part, which is dependent on the total angular momentum n, and the second part which depends on my projection of the angular momentum onto the a-axis, and the prefactor is something that is obtained from the difference between the rotational constants a and b. Okay, so this is how we can derive this energy dependence, rotational energy, as a function of n and k. And I can do the same thing for the Oblate molecule as well. However, here it makes sense then to look at the only uniquely defined axis in terms of moment of inertia, namely the one that is largest, because the others two are smaller but identical. So I look at the projection of my angular momentum of the vector n onto the c-axis, and I'm calling this, in this case here, k. And the formula looks similar. It's just that here I have now c minus b as my term that appears in the energy expression. And yeah, so that is the Oblate case. Now, this means for polyatomic molecules, my rotational energy will depend not just on the actual angular momentum, but also on its projection onto some internal axis of the molecule, right? So if you have a look at this diagram in the upper right corner, this is energy in some units. As a function of n, my angular momentum quantum number, and k. And here you can see that we get some energy distance or energy spacings in the case where k is 0. So we are in this ProLight case here. K is, for example, in this first row here 0. In the second one, it's 1. In the third row, it's 2. So this would be, for example, a rotational state where n equals 2 and k equals 2. And what you can see is that with increasing k, my energies in rotation go up for the ProLight case. Can anybody of you explain to me why we have a rising energy with an increase in the projection?
Because we get to a higher moment of inertia.
So you're on the right track, but there's one last thing that you have to tweak. So you're right, it has to do with moment of inertia. Obviously, this is changing with respect to projection, but look what it says. When k goes to higher values, in the case of the ProLight top, it means that our angular momentum projects more and more onto A. But what does it mean if we project more on A for the moment of inertia? It
goes down.
It goes down, yes. And so we have to make another addition to our thought that the rotational constant is. How is the rotational constant related to the moment of inertia? It's
inverse.
Inverse, right? It's inverse. So when the angular moment, when the projection gets larger, this means that so this vector n has a larger projection here onto the a-axis, and our moment of inertia gets smaller. But when the moment of inertia gets smaller, then the corresponding rotational constant gets larger, and therefore the energy splitting goes up. And this is why in the ProLight case, with increasing k, we get a shift to higher energies. For the ProLight, for the Uplight case, it's the other way around. Why? Because here we have chosen the moment of inertia axis C as our reference, because this is the unique one, is the one with the highest moment of inertia. The others two have a lower one, but identical one. So the projection onto IC is what we denote as K, and the larger the projection goes, or the larger the projection becomes, the larger the moment of inertia will be, and therefore the smaller the rotational constant. And this is why here the energy spacings will be smaller with increasing K. Okay, so this is a little challenge in thinking it through, but I'm glad that you are still with me here and following this. Okay, great. So this is the symmetric top, but then I said 4 types. So we had linear, spherical, and symmetric. There's one last type, which is the slightly unfortunate one. It's the one that has the lowest, the lowest symmetry. Before I get to this one, there's another thing I wanted to comment on. It's on the degeneracy. Here I still have the degeneracy with respect to how the angular momentum is oriented in my laboratory frame, right? So this doesn't change the actual energy of my molecule. Doesn't matter how the angular momentum is arranged, but it is obviously, it is given by the following thought that comes in. If you look at the energy expression in the case of the symmetric top, you see that the value of K comes in squared. And so if you look at possible projections of N onto K, onto the C-axis, then you see that for a fixed value of N, there can always be two orientations that give you the same projection onto the z-axis, namely one that goes in the same direction as the z vector and one that goes into the opposite direction, right? Because of this square that comes in here in the energy expression, it doesn't matter how it's oriented, right? So for each so as soon as k is larger than 0, so at least as soon as there is some projection onto the z-axis, there are always two possibilities for the angular momentum n to be oriented in the molecule that give the same energy. And therefore, I have 2 times 2n plus 1 as my number of degeneracies for the symmetric top. So in the linear, we only had 2n plus 1. In the symmetric top, we had 2n plus 1 times 2. And for the spherical top, we had 2n plus 1 times 2n plus 1. This is just a technicality, but it explains the distribution of intensities in the rotational spectrum of these molecules. That's just something I want you to at least have heard about once. And the final class of molecules that we have to discuss are these asymmetric tops. And so these are molecules where our 3 values for the diagonalized moment of inertia tensor are different. So IA is different from IB, different from IC. And in this case, this can't be solved in a closed form. So the typical approximation that is often chosen in spectroscopy is to either do an interpolation between a prolate and an oblate shape. So if you look at the molecule, say, yeah, I mean, it's not perfectly prolate, but it's pretty close to prolate. So it has most likely a splitting of its rotational energies that is similar to what we find in a prolate. And so you can do an interpolation between these two shapes, prolate and oblate, by looking at how the spacing would be in the prolate case, how would it be in the oblate case, and where I am approximately. You can also do it in a more rigorous way by trying to solve this via a set of eigenfunctions of the symmetric top. So you make a combination of so a linear combination of eigenfunctions that you gain from symmetric top for prolate and oblate, and solve or try to diagonalize the rotational Hamiltonian in these bases. So that would be the mathematical way of treating that. So you choose a basis, then your rotational Hamiltonian becomes a matrix in this basis, and then you diagonalize this. So this would be your classical, or not classical, but your usual way of dealing with problems of this kind in quantum mechanics through the procedure called the Ritz type, where you just take, it's a variational principle actually, where you try to find in a given vector space the vector that gives you the lowest energy through this diagonalization of the operator that you're interested in this basis, right? So that would be the mathematical way of handling this situation in case of a less symmetric molecule. Okay, that's it for rotation. And we can move on to vibration as the other degree of freedom in the nuclear motion, which we also have now to extend to the polyatomic case. So this will take just a few minutes. It's a very quick extension. In the diatomic case, we said we only had this distance between the two atoms as our degree of freedom. So it's a single harmonic, one-dimensional harmonic oscillator picture, quantum harmonic oscillator in our approximation through a harmonic potential. Now for nonlinear molecules, we have 3n-6 degrees of vibrational motion. We've been talking about this in the past. We said we have per atom in Cartesian coordinates, we have 3 degrees of freedom, x, y, z. So 3 times n if we have n particles, and then we have to subtract the 3 translational and the 3 rotational degrees of freedom of the total system, because it doesn't matter how our molecule is arranged in space and where it is placed. So this leaves us with quite a few degrees of freedom if we have a molecule like this, right? So this has 6, 7 atoms, right? So 3 times 7 minus 6 is quite some number already for such a tiny molecule, right? And if you have something with hundreds of atoms, you can see that this quickly opens up many, many degrees of freedom in which energy can be deposited. How are we approaching this? And no matter how many degrees of freedom we have, it's always the same maths. We have within the Born-Oppenheimer approach, a potential energy surface, and we said this potential energy surface is a surface, is a function of my 3n minus 6 vibrational degrees of freedom, because this is what determines all the possible ways of how these atoms can be internally arranged. What I'm doing now is I'm again starting a Taylor expansion of our potential energy surface at this global minimum geometry. So, for example, this is my global minimum geometry. At this point, I'm looking at the potential energy surface by making small variations in all these coordinates, and get a approximation. So this is the value at the potential energy surface at the equilibrium. Then this would be variations first order. This would be second order. Here comes in the so-called Hessian matrix, the second derivative with respect to the internuclear displacements. And so, let me just okay, and so the first derivative obviously vanishes, and we have the total energy, the total nuclear energy in vibration in this set of coordinates, where we have already sort of taken away those coordinates through some transformation. I'm not going into details here, but at first we would have to get out these parts of motion that correspond to the actual translation of the molecule and the rotation. So they have to be eliminated through some coordinate transformation. Then I'm stuck with the remaining coordinates. And this is my energy expression in these remaining coordinates. Another thing I'm doing is now I'm introducing mass-weighted coordinates. This is just a certain cosmetic measure that I'm taking. I'm saying a QI is this coordinate that remained after projecting out my rotation and linear motion, multiplied by the square root of mi, with mi denoting the mass of this atom I that I'm moving. And after this transformation, I'm ending up with our energy expression in this mass-weighted coordinates, which are written as q. And so I have for the energy these two contributions. One is the kinetic energy, second derivative with respect to changes in this coordinate, and this potential term, which is here abbreviated as Vij, right? So this would be this second derivatives of the potential energy surface with respect to changes in these directions, Qi, Qj, and so on. And in general, there will be lots of coupling elements. Vij is zero, is not zero, so they're all mixed. But I'm seeking now a set of coordinates which decouples the problem. So I'm basically looking for a set of coordinates now, uppercase Q, which diagonalize my Hessian matrix. Okay, so what I'm doing is I'm taking the Hessian matrix and I'm diagonalizing this matrix, and use then these eigenvectors as my new basis. So if I take these eigenvectors as my new basis, in this basis, my Vij is now a diagonal matrix. And the big advantage is that in this case, after having performed this transformation, my set of differential equations for the QIs is decoupled. Because after transformation, V is now diagonal, and this is indicated by this omega here. So this is a diagonal matrix, has only entries along the diagonal, and I can, in vector matrix style, I can write down my energy expression as this term here, 1/2, and then the product of first derivative Q, first derivative Q, plus, and then 1/2. And here, since I have in Q my potential, so this matrix here is diagonal in my set of coordinates Q, I can simply write this as a sum over the entries along the diagonal. And we can see that our energy expression in these coordinates, when assuming that expanding to the second order is sufficient, I'm getting a sum of terms of sum over I, with I denoting my degrees of freedom for this vibration. So I have first, second, third, and so on, up to 3n minus 6. And if this is our energy, you can see it is fully decoupled. Our vibrational wave function for these n atoms is a simple product of one-dimensional harmonic oscillator eigenfunctions, one of them for each vibrational degree of freedom, which corresponds to some internal coordinate Q. So I'm ending up in this approximation. If I say it is enough to expand to second order, in this case, the problem decouples, and the total vibrational energy is simply the sum over the energy contributions of each of these decoupled one-dimensional harmonic oscillator oscillations. Each one of them corresponds to one type of vibration that this molecule can perform. I give you an example. Okay, it's coming up. Let me fast forward quickly. So this would be the example. Here you can see already for a molecule consisting of 3 atoms, this would be the 3 vibrational modes that we get. Okay, because it's 3 atoms. 3 times 3 is 9, minus 6 giving us 3 internal degrees of freedom. So there are only 3 types of vibrations that this molecule can perform, and this is how they look in so-called normal coordinates. Okay, just quickly, how do we get there? So I said this is how our energy expression looks like, and you can see already, I mean, it is an Hamiltonian that describes the one-dimensional harmonic oscillator, and the next slide is only dedicated to how are we solving this standard problem of quantum mechanics. This is here shown in a bit more in a fancy way through the Hamilton formalism, where I can say the first derivative of the momentum of the generalized momentum P equals minus, and then the first derivative of the Hamiltonian with respect to the to Q leads to our set of equations describing the motion, and we can see what we obtain is our standard form of the harmonic oscillator in the Newtonian standard form of writing it, right? So for for our coordinate qi for the vibration qi, so for the ith vibration in the system. And the solutions are the harmonic functions in linear combinations. So we can write it as E plus minus E I omega t, and the corresponding energy is simply the energy of the harmonic quantum oscillator. And yeah, so as I said, this is how the vibrations would look like in the case of a molecule consisting of 3 atoms. And one thing we should remember or keep in mind is that the normal vibration as we describe it here, so in this normal coordinates qi, is one way of how we can describe any type of geometry change in a molecule through a linear combination of these 3 vibrational motions, right? So if I combine them, I can also imitate a motion that just concerns a single atom of these 3, right? So it's just one way of a basis which I choose for describing potential changes of the geometry. And what makes these normal vibrations stand out through how they are derived is that normal vibrations are always delocalized, so they are concerning all the atoms of the system, and it's an in-phase motions of all atoms, right? So they all, if you look at the motions and the changes with respect to the equilibrium geometry, then these are all in phase. Yeah, this is a consequence of the maths that we did, because it follows from how we approach this by diagonalizing the Hessian matrix and solving then this by decoupling. Okay, so that's on vibration. We now know for any type of more complicated molecule, we can make this approximation by doing a Taylor expansion of the potential energy surface to second order, and then our problem falls into pieces. Basically, our ansatz for the total vibrational wave function is a simple product of one-dimensional harmonic oscillators, but obviously in each degree of freedom. For example, if you look at this first vibration here, it's one that makes an elongation of the triangle. It's at some point it's an equilateral triangle, and then it gets squeezed. So it's still symmetric with respect to this axis, but it's slightly elongated, right? So this is one type, and it will have a certain vibrational frequency, so some curvature for the harmonic oscillator that describes this type of vibration. And here on the other side, you can see a motion which is typically called the breathing mode of the molecule, because it's fully symmetric. It opens and closes again. And this type of vibration will have a slightly different curvature and therefore different spacings of vibrational energy. And if you have a gas of these molecules at a given temperature, then these states of vibrational excitation are occupied as described by the Boltzmann distribution, right? So at a given temperature, you have a certain probability for having these states filled. And obviously, if vibrational energy spacing is larger, then it will be less likely to be filled than somewhere the spacing is lower, right? So depending on your temperature and on these actual types of vibration, so the curvature in these various directions on the potential energy surface, you have a certain spectrum which you can see when looking at this gas of molecules at a given temperature. Okay, so that's it on vibration, and with this I'm coming to the recap questions. Session code for today is VIOXZ, and I have to switch it on for you quickly. So, The first question is, which type of rotor is CH4? The second is, how would the rho vibrational spectrum change if we replaced 4 H atoms by 4 deuterium atoms? So make it a little heavier. And the last one is, which statements about the Hessian matrix of a molecular system are correct? 3 options. For a nonlinear molecule, it's an F times F matrix with F equals 3n minus 6. Then, at the equilibrium structure, all its eigenvalues are negative. And the option 3, at the transition state, at least one eigenvalue is positive. Okay, so I'll probably wait for another 10 seconds and then we stop. Question 3 is a little bit tricky in how it's formulated, so you have to think a little bit what it means to speak of an equilibrium structure as an extremal point on the surface and the transition state. What does it say about the Hessian matrix? All right, let's stop and see where we are. Okay, so there was a little bit confusion. Which type of rotor is CH4? Half of you made the right choice, a spherical top. So I wanted to build this molecule before, but then it would have been a giveaway for this recap question round. So this is CH4, and you can see that this symmetry is already sufficient for the system to have a moment of inertia which is independent of how you place the axis through the C atom, right? So this already has enough symmetry, so spherical top, the highest symmetry, is the correct answer here. Second one is, how would the rho vibrational spectrum change if we replaced the 4 H atoms? And so this was one of these where 2 answers were correct, namely the rotational lines are more closely packed. So 80% had chosen this answer. So you remember what we talked about. If the moment of inertia gets larger, then the rotational constant gets smaller, and therefore the spacing is smaller. But it's also correct that the band center shifts. Yeah, the band center shifts, because if you think about our vibrational energies, here we have this frequency omega, which is the square root of the curvature over m, k divided by m, and then square root. So if you change the mass of the particles which are vibrating, you are changing also the curvature of your quantum harmonic oscillator, and therefore the vibrational energies will have different splittings. And so the rotation sits on top of this, and therefore the band that belongs to one specific vibrational transition is at a slightly shifted place, right? Because also vibrational energy is affected. And finally, third question, which statements are here correct? And 90%, identified the correct answer for a nonlinear molecule. It's this F times F matrix with 3n minus 6 degrees. So that's fine. And a few were thinking about the other two options as well, because I formulated them in a way that sounds right and is just, I mean, it is wrong, but it's a little tricky. So at the equilibrium structures, all eigenvalues are positive. That's the case. That means that in any direction, when you go away from the minimum, you increase the potential energy. Otherwise, it wouldn't be a minimum as an extremum on the potential energy surface. And the other thing, the transition state, at the transition state, at least one eigenvalue has to be negative. Okay, because this is then the only, so a first order transition would be something like a saddle point if you want to cross a mountain ridge, for example, right? Then at the saddle point, in all directions, it will go up. Only if you follow the path over the saddle in this direction, it will go down again. So in this way, it would be a negative curvature, and so it would have at least one eigenvalue negative. Then it would be a transition state of first order. Okay, and with it, I thank everybody for participation. There will be time for questions, but I'm stopping the recording at first.